Section: Introduction. In this section, we discuss the significance of gaze in human behavior, as it reveals how individuals engage with their surroundings. Our visual attention reflects our intentions during daily activities and is crucial for social interactions. We learn to follow others' gaze from a young age, which helps us participate in joint attention. In conversations, gaze helps us understand who is being addressed or what object is being discussed. Therefore, estimating gaze targets is vital for creating systems that comprehend human behavior. Many previous studies have developed specialized architectures and datasets for gaze target estimation, often using a multi-branch design. This design typically includes a head branch that captures visual features from a person's head and a scene branch that analyzes the entire image. Recent advancements have also integrated additional data types, like depth and human pose. However, these models often rely on small datasets where human annotators label gaze targets, unlike tasks such as segmentation and depth estimation, which have thrived with self-supervised models trained on large datasets. We pose the question: can gaze target estimation benefit from a foundation model approach? In this paper, we demonstrate that pre-trained visual features from transformer-based models, like DINOV2, can be effectively utilized in a new architecture to achieve top-notch gaze estimation performance. We introduce our model, gaze estimation via large-scale learned encoders, Gaze-LLE, which offers two main advantages. First, it shows that a foundation model approach is viable for gaze estimation, allowing it to benefit from ongoing improvements in foundational models. Second, by using a robust general-purpose backbone, we significantly simplify the model architecture, reducing the number of learnable parameters and streamlining the training process. We illustrate these architectural benefits by comparing Gaze-LLE to the traditional multi-branch approach, which requires complex fusion of different learned representations and intricate training procedures. In contrast, Gaze-LLE utilizes foundational feature representations that can handle dense prediction tasks with simple linear projections, avoiding the need for extensive representation tuning. Notably, simply replacing the backbone in existing gaze architectures with DINOV2 does not yield good results. In fact, it often performs worse than the original models. Our solution lies in designing a novel Gaze-LLE decoder that adapts DINOV2 specifically for gaze prediction. We also analyze the challenges of using foundation models for gaze estimation and conduct extensive experiments to evaluate our architectural choices. Our contributions include introducing the Gaze-LLE architecture with a specially designed decoder for gaze target estimation, identifying key technical challenges, and validating our design decisions. The Gaze-LLE model is efficient, using only about 5% of the parameters found in most previous methods, while achieving state-of-the-art performance across major gaze estimation benchmarks. It also demonstrates strong performance across different datasets without needing fine-tuning and can be trained efficiently in under 1.5 GPU hours. We aim to release our code and models to inspire the development of even more advanced gaze estimators. In the related work section, we note that the prevalent method for gaze target estimation involves a multi-branch fusion approach, where an initial encoder feeds into multiple branches that extract specific gaze cues. These branches then merge to create a comprehensive representation, which is decoded into an output heat map. Our goal is to show that such multi-branch architectures are unnecessary and inefficient. We prove that we can achieve state-of-the-art performance by processing features from a frozen foundational visual encoder with our novel decoder, which is uniquely tailored for gaze estimation. We are the first to demonstrate the effectiveness of using a frozen large-scale encoder for this task, and our decoder design is innovative compared to previous gaze estimation methods. The multi-branch approach originated from Rekassens et al., who introduced the gaze-follow dataset and a two-branch architecture for estimating scene saliency and refining it for specific individuals. This method has been widely adopted, with later works adding more cues from auxiliary models. A key aspect of gaze estimation is integrating features from the target person's head with other scene cues to accurately interpret head pose in context. Multi-branch methods address this by using head representations as inputs to the scene branch, requiring separate encoding for each person and complex fusion mechanisms. Many also employ complicated multitask objectives for training, which can slow convergence. In contrast, we provide head position prompts as separate inputs to our unified decoder, allowing all scene cues to be extracted within the decoder itself. This eliminates the need for a separate head branch and the complexities of multitask objectives and fusion modules. Among multi-branch architectures, the two-branch approach by Tafosca et al. Is the most similar to our work, but we show that head analysis can be integrated directly into the decoder, simplifying the architecture further. Our Gaze-LLE model outperforms others with significantly fewer parameters. Some previous studies have approached gaze target estimation as a set detection problem, predicting head locations and gaze targets simultaneously, but this adds complications and often requires ground truth gaze data during testing, limiting comparisons. Other works have focused on estimating 3D gaze direction from facial features without identifying gaze targets, while some early methods estimated head orientation to find gaze targets. Additionally, research on social gaze behaviors, such as shared attention and mutual gaze, can benefit from our gaze estimation approach, as it naturally incorporates social context within a shared scene representation. Section Summary. In this section, we highlight the significance of gaze in human behavior and introduce our novel Gaze-LLE architecture, which leverages pre-trained transformer-based foundation models for gaze target estimation, achieving state-of-the-art performance while simplifying the model design and reducing the number of trainable parameters significantly. We also discuss the limitations of traditional multi-branch approaches and demonstrate that our unified decoder can effectively integrate gaze cues without the need for complex architectures. Section Gaze-LLE. In this section, we define the problem of gaze estimation using an RGB image and a bounding box around a person's head. Our goal is to predict a heat map that indicates the likelihood of each pixel being a gaze target. Additionally, for certain benchmarks, we also predict the probability that the gaze target is within the frame. We introduce our Gaze-LLE architecture, which includes a large, pre-trained scene encoder and a gaze decoder module. The gaze decoder focuses on a specific person, updates the features using a small transformer, and generates both the gaze heat map and the in-frame prediction. For training, we utilize a pixel-wise binary cross-entropy loss for the heat map. We create a heat map using a Gaussian distribution around each gaze annotation. When predicting if the gaze is in or out of frame, we employ a multitask loss that combines the heat map loss with the in-out prediction loss, making it simpler to optimize compared to previous methods. Our model, which uses a VIT-B backbone, has significantly fewer learnable parameters than earlier approaches. A crucial aspect of our method is the use of a pre-trained visual encoder, like DINOV2, as the sole backbone for gaze estimation. We explore various design choices and find that simply replacing the encoder in existing architectures with DINOV2 does not yield good results. Our experiments show that even when fine-tuning, DINOV2 does not outperform older, less powerful backbones, highlighting the need for our Gaze-LLE approach. We also investigate whether a separate head branch is necessary. Previous methods used a dedicated encoder for head crops, but we believe that DINOV2 captures gaze direction effectively on its own. Our comparisons reveal that performance is similar with or without a head branch when using a transformer decoder, but not with a convolutional decoder. This suggests that the transformer's ability to propagate global information is essential for extracting relevant features, leading us to our head prompting design. In terms of technical details, our model generates a gaze heat map of size 64 by 64. We use an input image size of 448 by 448 to capture fine details while keeping computational efficiency. We conduct experiments with frozen DINOV2 backbones and train our model on gaze follow for 15 epochs using the Atom optimizer and various data augmentation techniques. We then fine-tune our model on video attention target and child play with specific training parameters for each dataset. Section Summary. In this section, we define our Gaze-LLE model, which predicts a gaze heat map and the probability of a gaze target being in frame from an RGB image and a bounding box. We utilize a frozen DINOV2 encoder and a transformer-based gaze decoder, optimizing our model with a simpler multitask loss while demonstrating that our architectural choices significantly enhance performance compared to prior methods. Section: Main. In this section, we present the results of our Gaze-LLE trained model applied to different datasets, including video attention target, Gaze-LLE, and child play, without any fine-tuning. Our method shows strong performance across these diverse datasets and generalizes better than other methods that perform well on Gaze-LLE but struggle in cross-dataset scenarios. We believe this strong generalizability comes from using a flexible encoder that learns fewer parameters, which helps prevent overfitting to any specific dataset, and from not relying on auxiliary models that may not generalize well. We notice that our model experiences the most significant performance drop on Gaze-LLE due to two main factors: the substantial difference in domain, as Gaze-LLE features a unique retail setting where users seldom face the camera, and the different annotation method, where participants are instructed to look at specific objects rather than relying on human inference from images. Our approach achieves state-of-the-art results across datasets, outperforming Tonini et al.'s method, which requires in-domain data during training. We also explore the best placement for head prompting in the decoding process. By moving the head prompting to later layers of our gaze decoder, we find that this results in only minor performance drops. This adjustment allows us to achieve state-of-the-art results on Gaze-LLE while limiting person-specific computations to just the final transformer layer and two convolutional layers. This ability to reduce person-specific computation while maintaining strong performance could enhance efficiency in analyzing multiple people's gaze. Additionally, we test using head detections from YOLAV 5 instead of ground truth bounding boxes and find almost no loss in performance. Further details can be found in the appendix.